Alright, so at the end of the last video, I had started talking about using a capacitor to help rectify current, but I haven't actually talked about what capacitors are. So as promised in that last video, this is the video about capacitors. Oops, that wasn't a very good draw. Underlined capacitors. And the simplest type of capacitor is what is called a parallel plate capacitor. If you remember at the end of that last video, I had showed you that the electrical symbol for a capacitor is two parallel equilength lines, and the reason for that is because this is supposed to represent the parallel plates of a capacitor. And what you literally do is take two conducting plates. So this could be one plate like this, right? And then you take another plate and you put it next to it, not too far away from it, but with some space in between them. And then you connect a wire to each one of them. Okay? Then what I can do is I can start running current through this. And let's say I start current going in this direction. What that means is, as we think about the direction of current, current is the positive charges moving. That means over here on this left plate, I'm going to start to gain positive charges. I'm going to put a positive charge on there. And if this plate then has now a slight positive charge to it, what it's going to do is cause the other plate to experience a Coulomb repulsion to it, which means that what's going to happen is this is going to be positive. So what it's going to want to do is it's going to want to, if you think about it, it's going to want to drag an electron up to be attracted to that. So it's going to gain a negative charge. And then as I increase the positive charge on this left plate, the negative charges will then increase on the right plate to cancel it out. All right? And so what you'll end up doing if you keep letting this run is you can keep adding positive charges to this plate, and then it'll keep adding negative charges that are attracted to that, to the other plate. And what you then could do is turn off this current. You could turn it off, you could disconnect it, and this would then sit there with a charge separated. And if you have this charge separated, you now have a stored potential energy in there. Okay? I could then take this, so we'll say I started off with this attached to a battery, right? Let's say I had this attached to some battery like that, and I charged it up. And then I took and I removed the battery. And now I can use this. I've got charge separated. And you can imagine if I go and attach this to something, like say I attach this to a light bulb. All right, put a little light bulb here. I attach this to a light bulb. What will happen is, as soon as I attach it, this gives away for these negatives want to cancel out and want to get to those positives. They can't do it across the little gap. They're trying, but they can't. And now suddenly I provide them a pathway through the light bulb, around, and over to the side. Well, what are all the negative charges going to do? They're going to start to run along this wire up through the light bulb, and they're going to make their way over to here to cancel out. So I charged it with current going one way, right? So this current was going clockwise, which meant the electron flow was counterclockwise. And now I discharge it, and it does the opposite. The current will now flow clockwise, and the electrons, or I'm sorry, not the electrons, I'm sorry, I said it the wrong way. The current will now flow counterclockwise, and the electrons will flow clockwise. It'll undo itself. So we stored up all this energy, we got it there, and then as soon as we do this, it's called discharging a capacitor. It releases all that energy. It comes around here. All these negatives want to get over here to these positives. We give them an easy path to go across because they can't jump that gap. And suddenly we've stored energy and now we've reused it. And if you keep this in mind, you can go back to that last example in the last video at the end, and you can kind of understand now how this would keep the current going. Whereas the current was coming in, this would be charging up, and then when we turn the current off, this is going to run out through our device and try and come over here and discharge the other side of the capacitor. And basically, when the current coming in was cutting off, this would then ramp up, stop filling up, and all the current would come out of it and keep that electricity going for a brief moment of time in order to smooth that whole thing out. All right, so anyway, this is our parallel plate capacitor, and we're going to call, we need to define something here, because if you think about it, there's going to be a certain amount of charge that we can store on this thing before it gets so much on there that it's either going to break, or it'll get so strong that it can start jumping across this gap like little sparks of lightning would do. And so without breaking it, what we can do is we can define something called capacitance. And what this is it tells us the amount of charge, the amount of charge per unit volt that a capacitor can store. Okay, it tells us how much it can. Mathematically, that says capacitance, we use a capital C for it, is the amount of charge we put on there per unit volt. And so looking at this, you can see that if we increase the voltage that we're putting on this, in other words, we put a higher voltage battery on here, so let's get rid of this. Let's go back to having a battery on here, right? So if I put just a single cell on there, 1.5 volts, it's going to have a little bit of energy to force some charge up onto here, onto this plate, and get some negative on here. But if I start putting more and more cells and get a bigger voltage, then it's got more potential to shove more charge up on this one plate and therefore create more charge on the other plate. And so that brings us to this capacitance. And the capacitance itself for a capacitor is constant. Once you find the capacitance of a capacitor, assuming you don't break it or anything like that, that is its capacitance. Now, the actual amount of charge that is stored on that capacitor depends on how big of a voltage you use to force that charge on there. But once you get the capacitance of a capacitor, a non-changeable capacitor, that's all it is. Okay? It doesn't change after that. And then we can actually graph this out, right? If you think about this, I can rearrange this to be where do I want to write that? I can write it right below it. V equals 1 over C times Q. And so I can graph voltage versus charge on it, right? I can graph voltage or charge it, and then that'll be linear like that, right? Y equals mx, and 1 over c would be the slope, and so the slope here would be 1 over c. Okay, and that we could do. You could apply a certain voltage to it. I really should have flip-flopped it. I should have done Q versus V, and then the slope would be just C. I guess I could sketch that. I could have done Q versus V. Still going to be linear, but now the slope is just C. That would be Q equals C times V. And I could apply a certain voltage to a capacitor, measure the charge on it, then apply a voltage, measure the charge, plot that point, apply a voltage, measure the charge, plot that point, apply a voltage, measure the charge, plot, and just go through and do that, and then the slope that I'd end up getting would be my capacitance for that specific capacitor. One more thing, what units is this measured in? Well, it's a coulomb per volt. Okay, it's a coulomb per volt, so the unit is a coulomb per volt, not a capacitance, but a coulomb. I know that's a little confusing. A coulomb per volt and a volt, a coulomb per volt and a volt is a joule per coulomb, right? So we can start measuring, so this would be a coulomb, and that's a joule per coulomb. So this could also be a coulomb squared per joule, and ultimately we don't want to write all these different things, so we came up with just making this the unit of the farad. All right, capital F, it's the farad. I believe that's just F-A-R-A-D. But that's our unit for capacitance, okay, the farad. Usually 1 farad is actually a very large capacitance, so most of the capacitors you're going to see are going to be down on like the microfarad kind of level, and they're a lot smaller than that. Okay, now continuing on with this parallel plate capacitor. If we think about this, and I'm going to redraw this parallel plate capacitor here, and I'm going to draw it purely from a, well, no, I'm not going to draw it from a purely side view. Let's say here's our first plate, and then I'm going to make them a little bit more separated here. Here's our second plate. Okay, here's our parallel plate capacitor. There's the wire on one side. There's the wire on the other side. Okay, what things could affect the capacitance? Because all capacitors, they're all kind of different. So what things could actually affect the capacitance of this parallel plate capacitor? The first thing that's a big deal that can affect it is actually the size of the plates. Think about going to get dinner. The bigger your plate is, the more food you can fit on that plate. The larger these plates are, the more charge we can fit on there. So the first thing is area of the plates. Bigger the plates, the bigger the capacitance, the more we can fit on there. The second thing is their separation. How far apart are those plates? We'll call that D. And so the plate separation D of the plates. Okay, the closer they are together, the stronger the Coulomb force will be between the charges on them, and therefore the bigger effect they can have on each other and the more capacitance they can have. So closer these plates are together, the more capacitance you will get. And so those two things are very big deals, and we can actually go ahead and write them down. We can say that capacitance is going to be, well, I should say proportional to, but we're going to add something in here. It's got to get bigger. The bigger the area, the bigger it gets, and then the smaller the distance, the bigger it gets. So it's area over distance. And then we got one more thing. There's actually something you can do with this, and it's called adding a dielectric. So you know that the electric fields travel differently through different materials. So what you can actually do is fill this area in between them with a dielectric, with a material, a non-conducting material, not something that's going to short it and allow the electricity to flow between them and kill it. That would destroy it. It wouldn't work anymore. But you can put some sort of dielectric in between there, and it can amplify that electric field, make that electric field stronger, and therefore they have a bigger impact on each other. And we can basically say we can add a dielectric. Picked a slightly different green there. But add a dielectric, and that's at epsilon. Instead of epsilon naught, which was the permittivity of a vacuum, of free space, this is for inside a material. How does the electric field travel through that material? And so depending on what material you put between there, it can change capacitance. So how does some of this work? Well, your phones, most phones nowadays, smartphones, they all have those capacitance screens. It has this grid of little capacitors on there, and you're touching it and you're changing the capacitance as you do it. Another one is those plasma balls, right? Have you ever seen those things? It's got like the base, and then the base is shaped like that, and then it has that globe on it and that little thing in the middle. And it looks like that, and you see all the lightning come out of it, like the tendrils of light, and they move all around. Well, what this is a big giant capacitor, really. What this is one plate of the capacitor is that ball in the center. The other plate is the base, and what you're seeing is gas ionize as we get, this could be the positive plate, this could be the negative plate. We have the electric fields going around from one plate to the other, and then where the electric fields are the strongest, it's creating like a little plasma gas right there, right? And so you only see it inside the ball because that's the only place where it's actually ionizing the gas, but it's just ionizing along those electric field lines. And if you come along and touch it at one point, you're basically causing the capacitance to be really strong there, and you get a really strong electric field there, and it seems like all the electricity is coming to your finger, but what you're really doing is kind of like with your phone screen, is changing the capacitance in that direction, increasing that electric field, and then it's ionizing the gas more in the direction towards your finger. Another big one of these is what are called stud finders, and what you do with those is they're a very simple device. Is if you look in a wall, right? You have a wall, and behind the wall or inside the wall, you have studs every so often. You have, big boards that are placed vertically behind the wall. And if you have to hang something heavy on the wall, you have to find where those boards are because if you hang it in just the drywall, it will break. And so you have to find those boards. And so what you do is you take these parallel plates and you rotate them so that it's like one plate here and one plate here, right? So they're not facing right on each other, but rather the electric field is arching over from one to the other. I guess if I drew a side view, like here's one plate, here's the other plate, the electric field are arcing over this way now. And now you take this, put it in a little handheld device, take that, stick it on the wall here, right? You stick it on the wall, and let me draw an above view of the wall. So here's our wall. Oops, that was not good. So anyway, here's the wall, and here's the stud behind the wall, right? So what you do is take your little stud finder that has the two parallel plates here, and the electric field is going like this through the wall, and you move it along, and when you get your stud finder across a stud, that stud acts like a dielectric between the two plates. And it increases the capacitance, the charge changes on there, and then your stud finder realizes that there's a stud behind the wall. So it's a very simple device. It's just a little parallel plate capacitor that's looking for the capacitance to change when it goes across that stud, when it gets that stud behind it and it has a greater dielectric in there. Okay? So that's pretty simple idea for these parallel plate capacitors. Most capacitors you look at don't look like two plates. They look like little cylinders. Like this. If you look in electronics, some of them are wide and short, and some are tall and skinny like that. And then they'll have two little prongs coming off them. For these long, skinnier ones, they'll have it coming out of each end. But how do they make these? What they basically do is you want to reduce this a lot. So what you do is you want a really big plate area. So you take something like, and I don't know exactly the material, but you take something like aluminum foil, right? And you take and you put this big giant long sheet of aluminum foil down. And then you want a small separation, and you want a dielectric. So then you put something else. You sandwich a layer of something non-conductive, and I guess it could be something like saran wrap. And then you sandwich another long sheet of aluminum foil like this, right? And so you do these alternating layers of some of your conductor, your plate, and then your dielectric, thin dielectric like a saran wrap, and then another big long sheet like aluminum foil again. And you take these and you roll them up. You put them next to each other, so you have a huge bunch of area. You have a very small gap because, like saran wrap type stuff, very, very thin. And you have an also dielectric, and you take and you roll this whole thing up, and you roll it up, and you stick it in a little tube. You attach one of these wires to one of the plates, and the other wire to the other plates, and there you go. You've got your rolled up capacitor, but you roll it up like that, and so that's how a lot of these modern ones are made. Okay, and so they won't look like parallel plates, they'll look like little cylinders. All right, so enough of that. How do we actually go about using this? Now, before we talked about finding equivalent resistances, when we had multiple resistors hooked together, what we want to do here is find equivalent capacitance. And it's very similar to the equivalent resistance, but it's flip-flopped. So in series for resistors, you added up the resistors, you just added them up. For capacitors, you add up the reciprocals, which is what we did for resistors in parallel. Right? You just add them up. And so what this causes is when you have capacitors in parallel, like capacitor, 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 so on and so forth, however many you have, it causes an overall reduction in capacitance. For resistors, when we had resistors in series, right, it caused an overall increase in the resistance because you had to go through all resistors. Well, here this causes a reduction. If you think about it, there's a voltage drop across each one of these, and the overall capacitance is charge per volt. So what we're essentially doing is we're taking something like, so maybe we had 12 volts and it dropped down to 0 volts over here. Well, with just one capacitor, it would be that full 12 volts over there shoving charge on there, right? So if we look at this, we've got the charge is capacitance times voltage. So we're shoving it on there with 12 volts. And so we can get a lot of charge on there. But if we put several capacitors in a row, we get those voltage drops. So it might only be something like 4 volts on this one, 4 volts on this one, 4 volts on this one. Because in series, they're each going to cause a little bit of a drop. That means they each only get 4 volts on them. It reduces that voltage. It reduces the amount of charge each one can hold. And so it reduces the overall equivalent or effective capacitance of each of them while they're in series. So in series for capacitors, it causes a reduction. So you have to add them in reciprocals. It's kind of like how in parallel for resistors, putting a bunch of resistors in parallel reduced the overall resistance, and we had to add them in. We had to add them in reciprocals. We had to add the reciprocals of those guys together. But here, it does the opposite with this. So now think about parallel. In parallel, you're going to get an overall increase in capacitance. So for parallel, it acts like for adding up parallel resistors is like adding up for adding parallel capacitors, it acts like adding series resistors. You just add them up. And so in parallel, it'll look something like this. Oops, little line there. So let's say we have like some capacitors like that are all in parallel, right? Well, if you think about this, this could be, say, 12 volts here, right? 12 volts. I guess I could actually put this V on these. And this could be 0 volts here. Well, that means we have to have, if you think of Kirchhoff's law, the voltage drops, we have to go from 12 to 0 here. So this guy has 12 volts, 12 to 0 here. This guy has 12 volts. This guy has 12 volts. They all have 12 volts on them. And so, sorry, I messed that up. They all have 12 volts on them, so they all don't have a reduction in their capacitance. And the overall capacitance is then the equivalent is the charge that they're all holding. And if this guy can hold as much charge because he's still getting 12 volts, he holds his first full capacity, he holds his full capacity, he holds his full capacity. So then the total capacity is just all of them added up because they're all to their full potential for whatever voltage is applied to it. And so you add them up, and this increases the overall capacitance. This is like putting resistors in series. Resistors in series increases the overall resistance, and so you just added them up. Capacitors in parallel increases the overall capacitance, so you add them up. Up here, resistors in series decreased the overall increased the overall resistance, so you just added them up. Capacitors in series decreases the overall capacitance, so you add up the reciprocals. Okay? Add reciprocals, overall reduction. Adding them up just straight, overall increases. Capacitors in series reduces, add the reciprocals. Capacitors in parallel increases capacitance, add them up. Okay? And then think back to resistors. Resistors in series increases resistance, add them up. Resistors in parallel decreases resistance, add up the reciprocals. Okay? And it's a good way to check you too. You know that if you're supposed to add up a bunch of series capacitors, you should get an overall reduced capacitance, so whatever equivalent capacitance you come up with should be less, and whatever capacitance you come up here should be more, kind of like the flip-flop version of what would happen with resistors. All right, so I've got one last thing here. We're going to go back to that original graph that I had drawn, and we're going to talk about the energy in a capacitor. How much energy is actually stored in this? Because I told you it stores potential energy in there. And so if we look at this original graph, and we're going to go back to doing it this way. This is why I originally, drew it in this form before I redrew it in the other form. But I want it with voltage on the vertical, on the dependent, and charge on the independent, and we're going to have this here. And if we look at this, what we can do is look at the area underneath it, right? This area. And the area underneath it starting totally not charged and charging it up. Well, this area equals 1/2. It's a triangle. 1/2 base times height. So V times Q, or height times base, I guess in this case. And if you look at this, this is a potential energy per charge times a charge. So this is an energy, and this is in fact the energy stored in the capacitor. And so we can just rewrite this as E equals 1/2 QV. And then if we look at capacitance is equal to charge per volt. So this is a fine equation, but you can also combine it with capacitance is charge per volt, which tells us that charge is capacitance times voltage. So we can replace Q with C times V, and you get E equals 1/2 CV squared. So 1/2 capacitance times the voltage squared, and I believe that is the version of it you're given in your booklet. And there you go. This is the energy stored in a capacitor. You need to know its capacitance and the voltage you're putting on there, and it's 1/2 of it because of the shape of this graph. We get that 1/2. Okay, you can actually come up with that half through an integration way too, but this is an easy way to come up with it, kind of more just geometrically or algebraically kind of a way. Okay, I think that's pretty much everything for introducing capacitors. In the next video, which will be I think our last video for this whole topic, we'll cover actually charging and discharging capacitors, how they react as you start to push current onto them and when you first hook them up and stuff like that. Okay, so that's it for this.